Okay, this video is about the law of conservation of energy. And the law of conservation of energy is quite simple. It says that the total energy of a system is always conserved, meaning it's always the same. If you wanted to see it in mathematical terms, I would say that the sum of the energy at any one point in time, so the initial energy, has to be equal to the sum of the energy at any other point in time, so the final energy. So the initial energy has to equal the final energy. So lots of different types of conservation of energy questions. One of the more common ones involves a roller coaster. So let's suppose that we have this roller coaster and it has a mass of, let's say, 300 kilograms. And the height at point A is, let's say, 20 meters. And the height at point D is, let's say, it's halfway, so let's say it's 10 meters. And then we want to know what is the speed of the roller coaster here, assuming that it reaches the top of this first hill basically at rest, and it accelerates downwards, and then it's going to slow down as it goes up the hill. We want to know what is the speed at D. Well, we can use conservation of energy to find that. We're going to look at the initial energy at A and compare it to the final energy at D. So the energy that it has at A, well, it's at the top of the hill. We're going to assume that it's basically at rest. Maybe it has a slight forward momentum, but we're going to assume that it has only potential energy at A. At D, it's going to have both potential energy because it's 10 meters above the ground, but it's also going to have kinetic energy due to its speed. Now you'll notice that the mass appears in all three terms, so in this case we don't even have to include the mass. We can divide through by the mass. So substituting in, we get 9.8 times 20 meters. That's our initial energy. Then we have 9.8 times 10 plus 1/2 v squared. So the velocity here will work out to be about 14 meters per second. So all of this potential energy that it had at the top is converted into kinetic energy at the bottom, and then some of that kinetic energy gets converted back into potential, and we have the speed of the object at D. We could do the same thing if we wanted to find the speed at C. We just use conservation of energy again. So the initial energy, the energy at the top of the hill, has to be equal to the final energy at the bottom of the hill. This time mgh is going to be equal to 1/2 mv squared. It has no potential at the bottom, right? It's at the ground. So canceling off the mass and substituting in our values, we find that at the bottom of this hill, the maximum speed of our roller coaster turns out to be about 20 meters per second. Pretty quick. Now, suppose we actually got out there and had a radar gun or something that we could measure the speed. Do you think we'd actually measure 20 meters per second? Probably not. Not all of the energy at the top will be converted into kinetic at the bottom. Some of the energy is going to be lost. There'll be friction between the train and the track. There'll be energy lost in, noise and stuff like that, heating up of the train tires. So suppose we took a radar gun and we measured the speed. So suppose we took a radar gun and we measured the speed at C to be only 18 meters per second. How much work did friction do? Well, we can use conservation of energy again. At the top of the hill, we know it starts off with potential energy. At the bottom of the hill, it ends up with kinetic energy. But there is also some work done by friction. So all of this potential energy gets converted into kinetic and the work to overcome friction. Notice now I need to have the mass. The 300 kilograms is important because the more massive the train is, the more work that will be done by friction. So I put in MGH, it's 20 meters at the first hill. And we've used our radar gun to determine that the 300 kilogram train is traveling at 18 meters per second. And we can now calculate how much work was done by friction. And again, our calculator does all the hard work, and we find out that it's done about 10,000 joules of work. Okay. So the law of conservation of energy is useful in terms of calculating things like the work done by friction or how much energy has been lost. And again, you can compare any 2 points like we did here, comparing the A and C or A and D or A and B, whatever we want to compare. As the energy at one point compared to the energy at another point has to be the same when you factor in everything, including any energy that's converted into work to overcome friction. Okay, that's the basic law of conservation of energy. There's lots of different question types to look at. We can apply this to projectile motion, objects on inclines, all the stuff that we've done so far. So try some of the practice questions and let me know if you have any other problems.